Okay, welcome back. This is Math 0965. Oh, great, the stupid thing. Oh no, that was really screwed up. Okay, so anyways, what are we doing here is 7.1 now. And we're dealing with these things called rational expressions. And what are rational expressions? Well, look, right in this word rational, there's the word ratio. So ratio, you want to think of that as a fraction. So what we're dealing with are expressions that have a fraction bar in them, and they're also going to have variables as well. So it's not just dealing with fractions, but variable expressions. Okay, so what we saw with in the last section is kind of like we're factoring again. You learned how to factor in arithmetic, and now we factor with variables, right? And before in arithmetic, you learned how to work with fractions, how to add them, how to subtract them, how to simplify them. And by fractions, I just mean, regular old numerical fractions, right? So you may have saw something like this, and then you said, okay, we can factor the numerator and denominator, and then remove common factors. So 3 over 3 is the same as 1 over 1. 3 over 3 is the same as 1 over 1. 1 times 1 is 1. 1 times 1 times 2 is 2. And, okay, so we want to pull all the same game, do all the same sort of business, but with variables instead of just regular old numbers. So the first thing we have to worry about is this issue with division by 0. You cannot divide by 0. Okay. Okay, so an example of something we cannot do would be 9 divided by 0. You just cannot do this. Okay, so it's a no can do situation. And it's one of the main rules in mathematics. I don't know. It's like if you play football, you can't run out of bounds and then run it into the goal, right? Or run it into the end zone. So it's one of those kind of deals. Okay, it's just a rule. We all follow it, and if we didn't follow it, things wouldn't make any sense. The game just wouldn't make any sense. So that's our first goal. Because we're dealing with variables, we don't really know what's going on in the denominator sometimes. So here, this will be a rational expression, for example. We have to make sure that what we put in for x is not 0. Okay, so that's why it's an issue. It wasn't an issue before because we could always see what we have. It's not variable. In the top it's 1, and the bottom it's 2. Here in this expression, in the top it's 9, and the bottom, I don't know. It could be anything that we want to put in. Well, it can't be anything. We have to figure out what it can't be, and that's what the first section is in this 7.1. So it's excluding numbers. Basically, you're just trying to find the numbers for x that won't work, because that will cause division by 0. Okay, so how do we do this? The basic program is just to set the denominator equal to 0. A lot of times you can kind of inspect it and just know, all right, this isn't going to work, or this will work, sort of deal. Here's number 2 in the book. So we have 11 over 3x. So what number can't you put in for x? Okay, so we're thinking, what would cause this denominator to equal 0? So if you let x equal 0, 3 times 0 would be 0, and you would have division by 0. So we can't allow that to happen. Okay, so x cannot be equal to 0. So this expression would be undefined when x is equal to 0. Okay. Let's look at another one, 16, or actually it's just number 6. 17 all over 6x minus 30. Okay, now this one's a little more complicated. You could probably guess if x is 5, then it's 30 minus 30, which is 0. So you want to take this denominator here. If you really don't feel like going through the guesswork, you're having a bad day or whatever, you take the denominator and you set it equal to 0. Okay? And then solve that equation, and what you're going to end up with is the restricted value, the number you want to exclude. Okay, so if you add 30 to both sides, you get 6x is 30. Divide both sides by 6, and you get x is 5. So at the end of the day here, we have the restriction, and so how did we do this? We just set the denominator equal to 0 and solved. Okay, so that's going to be kind of our program for determining these excluded numbers. Set denominator. So we don't even look at the numerator really. It's denominator equal to 0. And then solve. Okay, so let's look at some more. Let's look at number 12. And I got a bit of a more complex expression this time. So we have x squared minus 9x plus 20. We're going to take this denominator and set it equal to 0. So this time, I don't think many of us could probably figure out what the number would be that would cause this expression to be 0. So it's almost like you have to kind of take it out and analyze it separately. So I take it, I set it equal to 0. Right? This is a quadratic form, so we hope we can factor it. So x and x, the signs tell me, the plus here would say it has to be plus plus or minus minus, and then that's dependent on this sign. Because this is minus, it has to be minus minus. Okay? And then I want two numbers that multiply to be 20, but add to be 9. So that would be 5 and 4. Okay. And then I can take each and set them equal to 0. So x minus 5 is 0, or x minus 4 is 0. And then add 5 to both sides. So x is 5 or x is 4. Okay. So these are the restricted values. We don't want to write x equals 5. It makes a little more sense to the reader if you put a little bar through those equal signs. Okay? X can't be 5, x can't be 4. And then you could kind of just leave it that way. Probably in the software it'll say something like x is undefined for the values 5 and 4 or something very official. Let's keep going, look at a couple curveballs and this sort of deal. So this is 14. Okay, so we have x plus 7 all over 7. Okay, there's no issues here. This time the denominator will never equal 0. 7 is not equal to 0. It doesn't get any simpler than that. So this guy is defined for all real numbers. If you had to write something, it's defined for all reals. Or if you'd rather, all real numbers. Okay, so sometimes they're going to work out for you. Let's look at number 18. So number 18, we have y plus 7 all over y squared minus 49. Okay, so this time we want to take that denominator and set it equal to 0. This guy is quadratic again. It's in our appropriate form, so we can factor it. It's a difference of squares. Has to be plus minus. And then what times what is 49? Well, 7. Okay. And then solve this equation. So you have y plus 7 is 0. And y minus 7 is 0. So either y is negative 7 or y is positive 7 are the bad places. Okay, so it's undefined. maybe I should write it out, right? Undefined for y equals plus or minus 7. We could write it that way. One thing to note here is that when it is equal to -7 and you like plop it into this expression, what would happen? Well, we can take a look. If I put -7 in for y, I would have this expression. Okay. -7 plus 7 is 0, and then -7 squared is 49, minus 49. And I have 0 over 0. Wow, that's a real mess. Okay. Some people think, well, because it's 0 over 0, that means it works out, and we don't have a rule for that or something. No, this is still undefined. We're not going to worry about the numerator. Okay, maybe if you took calculus or something, this would be an issue. But for us, we're just going to say, don't even worry about the numerator for now. Just set the denominator equal to 0 and get your numbers, and that's it. Okay, we won't go any further with the analysis for now. Okay, let's look at one more. Is number 20. It's kind of another curveball. 8 all over x squared plus 4. Okay, so the previous guy was a difference of squares. This guy in the denominator is a sum of squares, and you may remember how that worked, or in this case didn't work, right? So we're not going to be able to factor this thing. It's prime. There's nothing you can put in for x that's going to cause you to have -4 as an output, because whatever you put into x squared, if it's positive, it's going to be a positive times positive, which is positive. If it's negative, it'll be a negative times negative, which is positive. If it's 0, it's 0 times 0, which is 0. So 0 plus 4 wouldn't work. You just get 4. And in the other cases, it's going to be something positive. Okay, so you could never get a -4 in this position here, and so it's going to be defined for all numbers. You can put anything in there you want. Okay, so it's defined for all real numbers again. So that was another curveball. Okay, once we get that issue out of the way, we kind of like just sweep it under the rug, so to speak, and we start sort of going back through what you learned in arithmetic with fractions, right? So if you think about the progression that you learned with fractions, the first thing you learned how to do was probably to simplify expressions like this. Okay? So you would go, well, that's 5 over 5 times 2. 5 over 5 is the same as 1 over 1. And then you'll have 1 all over 1 times 2, which is 2. So the first thing you learned. And then you probably learned how to add them, or maybe even multiply them was next. So then you started learning how to multiply things. Okay, so maybe it's 1 all over 5. And we could reduce it like this. And we get 1 over 10. Then you learned how to divide. You just take the reciprocal and then add, then subtract. We got to go through the same progression now with variables. Okay, it's a bit tedious, but it's kind of interesting how they approach this. Is you take these items that you learned in arithmetic, and we just kind of smush in a variable, and now all of a sudden we're kind of working with generalities of numbers as opposed to just one number. It's very powerful. Anyways, I'll just shut up and we'll get in there and take a look. Okay, so section 2, simplifying. Okay, simplifying rational expressions. And the first thing we're going to be doing is just removing common factors. Okay. So the idea, recall, and I think I just showed you it, but we'll do another one. Recall this sort of deal where you would have something like 30 all over 27. Okay. You probably learned to do it in one of two ways: either factor it to death and then remove the common factors, or you learned to divide top and bottom by the common factor. So I think a lot of people kind of just think, I'm going to divide the top by 3 and then divide the bottom by 3. Okay? And that's perfectly fine. That gets the job done, right? So I have 10 all over 9, and that would be your final answer. You may have also learned this other way, and this is the way we want to do it now. Okay, so 30 is the same as 3 times 10. You're factoring. 27 is equal to 9 times 3. And then you see the common factors here and here. 3 over 3 is the same as 1 over 1. And then you're left with the 10 over 9. It's this this process here, which is more similar to the process with the variable version. So let's look at something from the future, so to speak. We'll have stuff like x cubed plus x squared all over x squared plus 3x plus 2. Okay. So you'll want to factor, and factor completely. Okay, so this one actually isn't factored completely. We could have rewritten this as 2 times 5, but I think most of us just sort of go as far as we need to go and then leave it, you know. But now you probably want to factor completely. So what does that mean in the numerator? That means pull out the GCF, which is x squared, leaving us with x plus 1. Downstairs, we'll have to factor into 2 binomials if possible. X and x. Signs have to be plus plus. And then the only factorization for 2 is 2 and 1. And spot check that in your head. So x squared plus x plus 2x is 3x's, and then plus 2. Okay, so FOILed it back out. It worked. Now we want to remove common factors. So what that means for us is to remove common binomials, or if there are any factors that look like this, remove them. Okay, but they have to look exactly the same. So this guy and this guy are the same. And our final answer then would be x squared all over x plus 2. And that's as far as we can go. And usually they won't write it with these parentheses down here. I'm just kind of trying to, I don't know, help you wrap your brain around it a bit more. Okay, so that's one type. Let's look at another type. So maybe you would have something like 3 over 15. And how did you usually do that? So you would divide again, top and bottom by 3. And what would you end up with? 1 all over 5. Okay. In our new methodology, we want to completely factor. So 3 is the same as 3. 15 is 3 times 5. And then you see you can remove the 3 in the top and bottom. That's equivalent to basically dividing top and bottom by 3. Okay, so I'd get 1 here, 1 here. So I end up with 1 all over 1 times 5, which is 1/5. Okay, so again, I want to do it in this new context with variables. So I'll have something like x plus 1 all over x squared plus 3x plus 2. Okay, I want to completely factor this guy. So x plus 1 is prime, right? I can't factor that any more than what it already is factored. Downstairs, I can factor that in the 2 binomials. So I'll have x plus plus. Oh, that's the same as before, right? So it'd just be 2 and 1. And then we have a common binomial on top and bottom of x plus 1. So I end up with 1 all over x plus 2 times 1, which is just x plus 2. Okay. My only sort of guiding principle is completely factor. Right? Make sure you completely factor everything first, and then remove common factors. There'll be a couple issues, hopefully we'll see along the way that I can iron out for you. And There's one issue with opposite factors, which will just end up with a negative floating around that we'll also look at. Okay, so let's dive in here and look at what the book and what you're going to see in your homework online has to offer. So 9x squared all over 6x. Okay. So completely factor it. Maybe you could, this one's a bit easier. It's too easy, really. I can reduce the 9/6 by dividing top and bottom by 3. If you do the factorization method, though, what would that look like? It's 3 times 3. X squared is x times x. And then downstairs, I have 3 times 2, and then just times x. Okay. So you remove common factors. So you're always going with pairs. There's a 3 here and a 3 here, right? So I can remove those. 3 over 3 is the same as 1 over 1. There's an x here and an x here. It's the same as 1 over 1. And then we have 3 times x in the numerator. In the denominator, we just have 2. One equivalent way to write this, and I don't know why people have, I don't know why, I guess it's just the way we're taught. This is equivalent to 3/2 times x. Okay. How do I see that? Well, it's the same as 3/2 times x over 1. Okay. What the heck is x over 1? Well, x divided by 1, anything divided by 1 is just that anything right back. So you can rewrite this as 3/2 times x, or 3/2 x. Anyways, my point is this thing right here, and probably the next time we see this, you've forgotten it, right? But at least somebody along the way has told you that those two items are exactly the same. Right? Okay, anyways, that's really neither here nor there. Let's look at 26, and we have 3x minus 9 all over 6x. Okay. Some people get kind of amped up, and there's too much coffee in them or something. They're like, oh, I can just cancel this and this, and no. You have to factor first. You can't actually cancel into a sum or a difference like this and this. That won't work. Okay, you can only cancel into factors. So there has to have a multiplication symbol in there. And this thing isn't factored right now. Okay, we can pull out a GCF of 3. And then downstairs, if you wish, you can factor in the 3 times 2 times x. Okay. So now you can remove this common factor of 3. Before you couldn't. You can't just cancel this into this. You would have to cancel this into this and this into this. Okay, it has to be both. This is considered one whole thing. And if you don't see that exact same thing in the denominator, you can't get rid of it. Okay, so here we have one whole thing, two whole things. So there's 1, 2 things up here, and then 3 things in the bottom. And then you look for common things, right? So this is common. That's the same as 1 over 1, and that's it. There's nothing else you could do. So you're left with x minus 3 all over 2x. Okay. So again, a lot of people, and this is totally wrong, but I see it anyways, they want to do one of these jobs, right? They want to just cancel this and this, but you can't do that. That's a no can do right there. You cannot do that. You have to factor first. Okay, so factor first. Factor first. All right. Let's see what else is on the table. Well, we got a ton of them. All right, so here's number 30. Negative 21 all over 7x minus 14. Okay. Again, you can't just cancel the first things out that you see. You have to factor these things. So I have negative, if you wish, 3 times 7 all over, and you can factor the GCF of 7 out of the bottom. So I got 1, 2 things in the denominator, 1, 2 things up here. You can only cancel out the things if they're exactly the same, and there's no x minus 2 up here, right? Okay, so I can remove the 7s. And then I got negative 3 all over what's left over, the x minus 2, and then that's it. Then you're done. There's nothing else you can do. Okay? It's a sad state of affairs. 32. Right, so again, we want to factor first. So 5x minus 10, there's a GCF there of 5. Downstairs, the x minus 2. Okay, so now these guys are exactly the same. I can remove those, and you end up with 5 times 1 is 5 all over 1, but that's the same as 5. Okay, we're not going to write 5 over 1. That's just silly. Alrighty then, let's move to 38. We got x plus 2 all over x squared minus x minus 6. Okay. In the denominator, I'm going to factor out the two binomials. And, in this numerator, you want to think of that as one item. Okay? It has a plus sign in between the two numbers. That's one thing. If you don't see it in the denominator, you can't get rid of it. Okay, so x and x, it has to be plus minus, and then the number is 3 and 2, and I want the bigger one to be negative. Okay, so I'll put the 3 over here and the 2 over here. I'm going to FOIL it just to make sure it worked. X squared minus 3x plus 2x is minus 1x, and then minus 6. Okay, I'm good. There are x plus 2 factors here, so I'm going to up with 1 all over x minus 3. So you're going to start appreciating all that work you did with factorization, right? Because each one of these has like a couple little factorization problems embedded in it. That's the only way you can simplify. Okay. So again, here we go. We're factoring the heck out of it. I'm going to set up my parentheses, start filling in the blanks. The signs say plus plus. It has to be y plus plus. Then 4 times 1, but 4 plus 1 is 5. So 4 times 1 is 4. 4 plus 1 is 5. Down here, it's got to be y, and then plus minus. So 5 and 1, and then when you want the bigger number to be negative, so 5 over here and 1 over here. And then you can remove these guys, they're exactly the same, and you're just left with the y plus 4 all over the y minus 5. Okay, let's look at 52, I guess. So I got x cubed minus 125 all over x squared minus 25. Okay, that guy in the numerator is a difference of cubes. Guy in the denominator is a difference of squares. Okay, so we want to factor both. Remember your SOAP formula. So x, same sign, opposite, always positive. A is x, b is 5. Okay, so I'll have x squared, 5x, and then 25. Downstairs, I'll have x, and then plus minus. The difference of squares, I need 5 for both. And then it looks like we can just remove the x minus 5s, and then everything else stays. Be aware that sometimes they're not going to be factorable. For example, 56 will have x over x plus 7. Okay. And it just, again, it's this issue. You can't cancel something like this. Okay, there's one thing in the top, there's an x, and there's one thing in the bottom, the x plus 7. Okay, if you don't see an x plus 7 up here, you can't get rid of it. If you don't see just an x down here, you can't get rid of it. Okay, so there's no way to factor this thing. It's already simplified. It's in its simplified form. You're done. Okay. Just be aware that there's going to be those guys floating about. Finally, then we have the opposites. And essentially, again, you've sort of seen this before with something like -5/5, right? What we mean by opposites is that when you add them together, 5 plus the numerator plus the denominator, you end up with 0. Okay? When it comes to numbers, it's quite obvious what's going on. I mean, this is just going to be -1, right? But when you have variables involved, they don't look as obvious, okay? It's not as obvious what the opposite of x plus 3 is, okay? So now it's going to be a little more difficult because some things will look like opposites, but they're not opposites, right? So what is the opposite of x plus 3? The thing that you could add to it to make it equal 0 is -x minus 3, because you have x plus 3 and then plus in minus x minus 3. The x's would cancel and the 3's would cancel, giving you 0. Okay? So now this thing is actually equal to -1. So what's the issue? It's just because sometimes things look like opposites in variable land, but they're not. For example, x minus 3 all over -x minus 3. Okay, so you may think, hey, that's just equal to -1, but it's not true. Okay, this is not equal to just plain old -1. What is? Well, you would have to have -x plus 3. They completely have to have opposite signs on them, and then you can reduce it to -1. Okay. Okay, so it's a little funny like that. You'll be able to identify them visually after a while, though. You just note that each term has the opposite sign. Like over here, these guys have the opposite sign, but these guys don't. Okay, so it's not a -1 situation. Over here, these guys have opposite signs, and these guys have opposite signs, so it must be -1. Up here, these guys have opposite signs. These guys have opposite signs, so it must be -1. Okay, so let's look. Here's problem 60. I have x minus 7 all over 7 minus x. Okay. From what we just went over above, this is obviously equal to -1. Okay, so the opposite sign scenario is occurring here. Let's go through the math of it though, just in case, why is this true? Well, in the denominator, you can factor out a -1. Okay, so I'll factor a -1 out of this. And what happens? I have -7 plus x. Okay. Then I can rewrite the -7 plus x as x minus 7. And that's just a commutative law of addition. And then you can remove these guys, because now they're the same, and you're left with 1 all over -1, and that's just -1. Okay? So long story short, it works. You just want to do it sort of automatically. You don't want to have to go through all of the math every time, because that's going to slow you down. You're never going to go home. You're never going to go see your family again. Anyways, 64 x minus 7 all over x plus 7. So this is that other case. There's a no can do on this one. You can't make these guys opposites. Even if you did the factoring, pull a negative out of the numerator, and what are you left with? -x plus 7. Okay, so it's kind of like you can't ever get it to equal each other. If you pull out the negative, then these are correct opposite, but these aren't opposites. Leave the negative in there, these aren't opposites, but these are opposites. So it's like there's this balancing thing. You can never get it to balance out. So at the end of the day, there's nothing you can really do with this one. You just leave it like this. It is what it is. Okay? Let's look at, I don't know, 2 more. So number 70, we got x squared minus 4 all over 2 minus x. Okay. So in this case, I can factor the numerator, x minus 2 times x plus 2. In the denominator, I have 2 minus x. Okay. So hopefully after a while, you'll note that these guys are opposites, and you can remove them, but you have to replace it with a -1. Okay. So I'll end up with -1 times x plus 2 all over 1, but we don't write that. And then you could distribute the negative, so negative x minus 2, and that would be it. Okay, so I think we'll just leave it at that one, and we'll see you next time.